matrix type examples of linear maps, I call it. I just chose one example from the yellow book. It's a tutorial question 2. Now it's a new chapter, chapter 8. And it's a question with many parts. I just chose one part, part A. So the mapping there is the mapping of between these two vector spaces, two-dimensional, couple of complex numbers to the quadruple of complex numbers, and the mapping is given by this formula. So it's the result of every application of the mapping will be a column of 4 numbers. Here's the numbers: 3x1 take x2, double x1 plus 4x2, negative 3x1 and negative 3x2, and x2, like this. This is an element of my C4, given that my x original vector was the element of C2. You will see plenty of examples like this, and many of them will require you to show that this is a linear map. The good news, you can always do it in the same way. You can just make this one simple observation, one simple trivial observation. You can say that if you build a matrix A, with the elements 3, negative 1, 2, 4, negative 3, negative 3, 0, 1, if you build such a matrix, it's a matrix with 4 rows, 2 columns, complex entries in general, then this whole expression can be abbreviated down to a simple matrix multiplication like so. If you multiply this matrix by this matrix, so this is a 4 times 2 matrix, this is 2 by 1 matrix, the result will be 4 by 1 matrix, and that will be the entries of that matrix. And you can always just convert any example of this type in the yellow book to a choice of a proper matrix and the matrix multiplication. So instead of argue this in this way, I will argue that this is a linear map in this way. Here's my argument. If I apply my T to a sum of 2 vectors, x plus y, it means that I multiply x plus y vector by matrix A. Here's the place I borrow something from my past knowledge. We know that the matrix multiplication is subject to the distributive law. So I can I can open the brackets and do the expansion like this. Again, you see I make clear where the step where we borrow something from the past. And that is individual t of x and t of y. That's why the first property is satisfied. So this place, it's a matrix multiplication distributive law. That's the place where the matrix multiplication distributive law is used. And that is true for any 2 vectors from C2. And that's my argument for the second requirement of a linear map. If I apply my linear map to a scaled vector, which again in my matrix multiplication language is simply this expression. Here's the place which I borrow again. Here's the place where I borrow something from the past. This time I will use the matrix multiplication associative law, meaning that my lambda scalar can be taken out and put it like this, something you established when you studied your matrix multiplication. And here's my scaling of T. And that is true like this. So here, the knowledge we used from the past is the matrix multiplication associative law. And this is it. That's why this map is a linear map. If effectively, you can repeat these 2 lines without attachment to any particular choice of the matrix A or any particular choice of the dimensions of your domain and codomain. You can repeat these steps for any Cn and Cm, and that's what I'm going to fix as a lemma actually now, another lemma for you, which you can use as a reference when you do other questions in the yellow book. If I have a matrix of size Mn with scalars coming from the scalar field F, as usual, it's either rationals, reals, or complex numbers. And if I have a linear map which maps n tuples to m tuples such that it is simply given by multiplication. Any such linear map, and that's a special case of that linear map. Any such map, it will be a linear map every time. And the proof effectively these two lines which I have presented already, they have no attachment to this particular choice of the matrix A. They work in this general setting as well because they only rely on these properties of matrix multiplication, distributive law and associative law, scalar associative law. So every time I would need to justify that something like this is a linear map, I will make just a reference to this lemma. The interesting thing is that in finite dimensional settings, when you just have any type of linear spaces, linear map can always be sort of replaced with something like this. We're going to discuss this probably next time on Thursday, but so far here it is. Many other parts in the question 2 can be done by simply just singling out the matrix A and making reference to the lemma like this. Any questions?